All right, so hello from the future. As you may note, December 2024 is a typo. Okay, I can get started. All right, so I'll talk about some recent research on dynamic matching markets, and I think the problem has been remarkably well kind of introduced by Amin this morning, so I really build on the notions and the formal description he provided to be a little bit at a higher level in discussing the results. So broadly speaking, we want to think about how to sequentially match agents, let it be supply resources or customer queries who are forming a graph, an edge-weighted graph, and we have stochastic arrivals. So we have a stochastic process describing how these agents come to the market. So that's the kind of the type of problem that I have been thinking about. And as you know, there's an expansive literature on this topic from various angles, and my interests somehow lie at the intersection of two lines of research. So one is on online matching, and Amin kind of introduced some of the models that are presented and used in that literature, pioneered by the paper of Karp, Vazirani, and a long line of research on stochastic matching models, many of which have been authored by Amin. And the second line of research that I'm also interested in is taking a different perspective. I would call it matching cues literature, where the focus is not so much on performance competitive analysis, but on kind of positing some relatively simple matching policies and then trying to understand how they perform, how they behave in rather complex stochastic systems. And so today I'll talk about how to kind of somehow find a juncture between these literatures in thinking of using optimization-based matching policies in dynamic stochastic processes that describe the arrivals to the market. So I'll talk about two papers. And you can think of them as variants, deviations from the model that Amin presented. So the first paper will be about the dynamic arrival and departure process. So in many markets, we do have actually agents coming to the market constantly, having a certain patience, so staying in the market for some time in which they're available for a match and then leaving the market. So trying to understand how to design online matching policies, near optimal online matching policies in this type of environment. And the second paper will be about introducing correlations in the arrival process, trying to think of stochastic models where there is a correlation, underlying correlation to the arrivals, and how does that change the type of policies that we propose. And I think the overall kind of picture here is actually quite, I think, positive in the sense that it shows that a lot of the results and approaches that Amin presented were actually quite robust when we think about these different stochastic systems. And in particular, we have to rethink a little bit the type of problem relaxation, the mathematical programming relaxation that we use to analyze and to devise policies. So if you remember, Amin presented linear programming. So we have to think of slightly variants of that type of mathematical program. But we can do that in many cases, and then leverage the type of linear programming solution to come up with online on-the-fly policies which are trying to round the fractional solutions of these mathematical programs. And we'll see that that's feasible under some further assumptions. And if I'm honest, I kind of, in thinking about this talk, I was kind of forcing myself to choose about one of the two papers, but the battle plan did not survive the first contact with preparation, so I'll try to kind of give a kind of dive a bit into the specifics of some of these results, but also we'll skip some of the higher level picture. So the first work is on dynamic stochastic matching, so thinking of this notion of dynamic arrivals and departures, and this is joint work with Omer Saritach, who's a PhD student at LBS. He's been doing some interesting work on these dynamic matching markets, and he's currently on the job market. This is his final year in the PhD program. So what do I mean by dynamic? So for many matching markets, one ingredient or aspect that is very important is the timing of the matching decisions. Because as I mentioned, new agents come, enter the market, and leave the market. And in some sense, the matching policy that you're implementing is endogenously affecting the availability of the agents in the market, which in turn affects how good the matches are. So non-surprisingly, if you think about like carpooling or ride-hailing, one important element in the way the operations of the matching platforms are executed is that they make you wait. Whether you like it or not, to kind of wait for a couple of minutes, this is actually a very crucial design for these platforms, because by making you wait, they're building thickness in the market so that they can find suitable matches. They can increase chances of finding a high reward, low cost match between agents in the market. But then the question is, how long should the agents wait? How much waiting is good waiting and enables kind of, on average, on the long run, good performance in terms of maximizing rewards or minimizing costs. So that's the underlying question that we want to incorporate into the matching model that we described this morning. So I'll start by defining the model formally, we call it dynamic stochastic matching, and then I will propose some simple matching algorithms that have provable performance guarantees, so in the form of competitive ratios, approximation ratios. I'll get back to that later. And I mean, the punchline is like precisely in thinking of new mathematical programming relaxations that are suited to this type of dynamic matching markets, and then converting these solutions from these mathematical programs to actual policies. And these will be relatively kind of natural policies, like threshold policies, but in some cases, more complex policies, online correlated rounding policies. So I'll get back to that. And I'll skip, but we have also some numerical simulations where we leverage data from taxi demand to represent some of these policies and analyze their performance. I'll briefly touch on that. So let's start with the model. Okay, so the model has two ingredients. One is we have an underlying graph, edge-weighted graph. So that's the network structure. So we will think of this graph as we'll have different agent types. So each node, each vertex is an agent type, I, and we'll have costs between the agents. So Cij is the cost of matching I with j. Every time you do a match, you incur that cost. And you can do, they could be like self-loops. You can match agents. For now, I'm not imposing any restriction on that. So that's the first ingredient. The second ingredient is going to be an arrival process. We need to model how the agents come to the market and come to being available for a match. So here, by the way, when I say type, you can think in carpooling. This can be different riders which have an origin, a destination, and some willingness to wait in the system. So now we have to specify the dynamics of the market. Okay? So what we'll use here is a relatively simple assumption. We'll think of that there are Poisson arrivals to the system. So there's a rate lambda I at which agents show up at each queue or at each vertex. And once they arrive there, they start waiting, and they abandon with the rate mu I. So they have an abandonment rate. So each of them has kind of an exponentially, independently sampled exponential duration in the system or sojourn in the system, after which they leave the system. And one of the challenges is the platform doesn't know how much agents are willing to wait. They might estimate mu, they might know mu, but they actually know mu, but they don't know the realization. Okay, so the name of the game is now we see all these agents pop up, and we have to decide not only who to match with whom, but also when to enact, when to execute these matches. Because that's also a crucial difference with previously, is that now there is this timing element that we have to incorporate in our decisions. So there's, of course, a cost if the agents leave before they are matched. So there's going to be an abandonment cost that is incurred per agent who leaves the system unmatched. So these are all the ingredients of the model. And if you think about now what it means to design a policy, well, what we're facing is essentially a Markov decision process, a dynamic program. So this morning, wrote explicitly the kind of online optimum, which would be satisfying the Bellman equation. Well, this is essentially a similar type of problem that we have here. One difference, however, is that we will be looking at steady state, because this is a continuous time model, and we are either minimizing long-term expected average cost or maximizing expected average reward. Okay, so that's the objective, and we want to find a policy that is competitive against these quantities, the optimum online policy. Okay. So obviously this is a problem that becomes combinatorial and quite complex, because we have the state space that describes who are the agents waiting. And if you think about the problem that kind of was described this morning, and trying to highlight a little bit the differences between the classic online matching setting and this setting. So they're fairly similar, and you can think of them as variants of one another, but one of the key differences is that in classical online matching, you have this separation between online agents and offline agents. So the offline agents are the resources, the ones that are waiting, and their availability is your state space. So whether an agent is still available for a match after T period was the state variable that Amin used in formulating the Bellman equation. But here we have dynamic arrivals, so in the sense that we can have arrivals potentially on both sides of the market, and each agent will stay for some time before they leave. And of course, this word dynamic is a bit contentious, so what I mean by this is really Poisson arrival and memoryless departures. Now, there's this interesting question also of when to match, and this is perhaps one element that kind of most differentiating of these two models. So in the classic online matching setting, when a customer pops up, you have an opportunity to match, and then it's done. You move on to the next customer arriving. In this case, we do have like some form of stopping time that we have to solve at the same time. So because we have this inventory, this stock of agents waiting at the different queues, and we are choosing when we want to make the matches, okay? And then in terms of the objective and the horizon, so this was a finite, and here we're looking at steady state, average cost. These differences are less important, I think, for algorithm design. And then the question is, what can we do in this environment? So can we come up with policies that are approximating the optimum online? Can we be competitive against an offline optimum? So in hindsight, someone that knows all the sequence of arrivals and trying to solve the offline optimum. So these are the type of questions that we'll try to raise. So any question about the model? And if not, I will. Good. So I'll start with mentioning one class of policies that is actually very natural and very much used in solving these types of problems in practice, and there's also a rich theory behind it, and these are batching policies. So what is the idea of batching? It's probably the most kind of natural way of thinking about this problem. This is a kind of multi-stage, like a dynamic program, but maybe we can reduce it somehow to an offline problem. And that's the idea of batching. So what batching is doing is it's going to wait for a batch window. So it's going to wait t units of time, and after those t units of time, it looks at all the agents in the market, and it tries to find an assignment or matching that minimizes cost under maximizing cardinality, or that maximizes reward. So that's a very natural policy to think about, because it kind of enables this reduction to an offline optimization problem. And here, what's the critical parameter is, of course, the batching window. So if you wait longer, you can accumulate more agents, and you can hope to maybe achieve higher quality matches. But if you wait too long, of course, there is a risk of abandonment, that the agents start leaving the system. Because the abandonment cost will grow. So that you have to tune kind of appropriately these two quantities. So and there's literature, previous literature, rich literature that looks at this both kind of in simulation, but also with one of Amin's papers showed that if you're maximizing rewards, you can actually prove guarantees, competitive ratio guarantees for this type of policies. But it turns out that if we're in the minimum cost setting, if we're trying to minimize cost, this policy actually cannot achieve a constant factor approximation guarantee, even if you tune the batching window appropriately, even if this batching window is picked optimally to balance between the two costs that I mentioned. And I think, of course, this type of results are in the worst case, and this policy I expect would behave very well in practice. But I think it's interesting to look at why, what is the underlying phenomenon here? And the idea is mostly that it's actually a relatively simple type of example. So imagine that you have a market where you have two types of agent, and these types of agents are not synchronized, like they're on different time scales. What I mean by this is that one of them arrives very, very frequently. They have a homogeneous abandonment cost and abandonment rate, and one arrives less frequently. And you want to avoid matching, doing these sort of matches. So you want to only match within the same time. Like imagine that this is associated with very small cost, maybe a kind of vanishing cost, zero cost. So well, you cannot pick a batching window that would work for both types of agents at the same time, and you will be incurring some costs by matching agents 1 with 2 sufficiently frequently that it kind of leads to high costs. And I think it's quite simple to fix batching for this particular type of instance, but it tells you something. It tells you that if you have a network, and in this network, some agents are kind of require more time to be able to form suitable matches, and others are on kind of higher frequency and maybe higher abandonment rate, it's going to be hard to achieve both things having a single kind of batching window. And that's kind of an intuition in terms of how, when we come up with other policies, they will be able to address this type of challenge because they will leverage local information about the market. So now what I want to kind of dive into is a bit more about how do we analyze this type of system and what kind of policies do we propose, and kind of really building on the framework that Amin presented this morning. So the first thing is, how do we measure performance? What is the suitable relaxation of this problem? And here we propose a linear programming relaxation, which you can think of as a kind of related to the linear program that Amin wrote here. So imagine the key in kind of idea here will be to distinguish between two types of vertices. Like suppose you're given a certain policy, we're going to distinguish between passive and active vertices. We say that an agent is passive if he's matched with, or she's matched with a vertex that arrived earlier. So that's a passive agent. So someone who gets matched with someone who arrived earlier, and anyone else is active. So why this wording, it comes from previous literature, but it's like if you're active, you're actively waiting to be matched. So that's where this notion comes from. And then we're going to introduce a decision variable, xij, for the match rate between active type I and passive type J agents, induced by that policy. So you have some policy that's going to induce some xij. And what I want to write down is a linear program that is a relaxation of all, the collection of all feasible policies. So first of all, once I have these xij's, if this is truly a policy that describes the rate at which these matches occur, I can write the objective. It's just a linear objective. And then the type of constraints that come next is coming from this notion of kind of fluid relaxation or flow balance, that any agent that comes to the market will either be passive or active, or will abandon. So I can write this equation that lambda I will be the sum decomposes into these different terms. So now, and this is kind of what some of the queuing literature refers to as, like, say, the fluid relaxation of this problem. Now, the interesting question is, how do we add abandonments on top of that? Because, again, the trade-off we're facing here is between abandonment and achieving high-quality matches. So the abandonment will come as relatively simple constraints that we incorporate into this LP to make it tighter, to make it a better approximation for the underlying process. So what are these constraints saying? They're saying that basically the level of abandonment of any type I will be related, will be like lower bounded by the rate at which I'm able to match active type I agents with passive type J agents up to some multiplicative factor. And this really comes simply from looking at the, kind of the DP and analyzing the DP between consecutive stages. You have to have, you can think of this as the physics of the system as such that you have to have this minimal level of abandonment incurred by any policy. Okay? So now this defines a polytope and a relaxation. So the question is, how good is this relaxation? Can we hope to come up with constant factor approximations in the same spirit as what was presented this morning? And if you remember, like the notion, there are two notions to measure performance. One is competitive ratio. So I'm comparing myself to the optimum offline. So imagine that there's this prophet, can look in hindsight at the entire information about the arrival process and then solves the matching, knowing everything. And then there's going to be a different notion, maybe finer notion, which is the optimum online. So here my performance is the ratio between my algorithm and the optimal solution of the dynamic program. So if I have this dynamic program and I have infinite computational power, I can actually compute that policy and that I can calculate the cost. So this is the optimum online, and that's another, the other performance metric that Amin mentioned. So our finding is that actually for the mean cost problem, for this setting, we cannot achieve a constant factor competitive ratio. So we cannot have competitive algorithms. The exact knowledge of the sequence of arrivals and departures allows the offline optimum to achieve a much better performance. Okay, so there's a lot of value in that information for the mean cost problem. So unfortunately, there's a kind of a negative result. We cannot hope to achieve that. However, I'll now kind of turn to more positive results. We're still able to kind of obtain a constant factor approximation ratio for one setting of interest, which is a spatial graph. And as a setup, as a motivation, I mentioned carpooling and ride-hailing and delivery services. So what these have in common is that the costs are kind of embedded in the metric space, so they satisfy triangle inequality. And with this type of assumption, we can actually devise policies for the problem that have a factor 3 approximation ratio for these special graphs, with the additional assumption that departure rates are uniform, that the agents leave the system at the same rate. Okay, so this is quite a bit of assumptions, and the result is not, I would say, admittedly, like extremely general. But I think I want to kind of emphasize that the policies, the underlying, I'm not going to delve too much into the specific. I want to focus on the different parts of our results. But the policies are actually quite natural, and that's, which is, I think, an interesting finding. So the policies that we can propose for this are threshold-based. So imagine that every agent, there's going to be a radius around this agent that is drawn. And if the agent starts waiting, becomes active, basically we are restricting attention only to the future arrivals within that radius. Okay, these are close enough agents. And then when an agent shows up, we will try to match that agent with all the active agents that whose radius, whose ball contains that new agent. Okay? And if there is contention between them, actually we can show that this is not much of an issue. We can just resolve the contention. Okay? So that's one type of policy that leads to this result. And another type of policy is putting essentially a price tag on each agent type, which you can think of as the value for the future, and then using that to construct an additive approximation of the value function. So in the DP, you can think of making decisions between matching now or waiting for later. And that waiting for later, that's the reward to go. So imagine that each agent, so the same value that we used for the threshold, we could use as a marginal cost for that agent in regards to the future arrivals. So these two policies can lead. I mean, in the simulations that we've done, actually this additive approximation turns out to be more effective than hard threshold policies. That's expected perhaps because these are smoother kind of decisions that we're making. All right, so how do we get this threshold or this marginal cost? Well, it's actually a surprisingly simple notion. Imagine that you look at just one agent and you're trying to do the best for that agent. So for that agent, there is an abandonment, a risk of abandonment, and there is an ability to match with the future. So if you try to balance these two, the optimal policy is a threshold policy because you just have one agent to deal with. There's no network anymore. And that can be solved efficiently in polynomial time, and this is how we get these thresholds. This is how we get the notion of marginal cost per agent that we use to inform the policies. So we did some simulation. I don't want to kind of delve into that. Maybe if there's questions, I'm happy to get back to this later. And I want to just present actually a kind of main result for more general networks. And as you'll see, kind of the result has a flavor that is more similar to what Amin presented. So in the reward maximization problem, so now imagine that there is rewards that we want to maximize the long-term expected rewards from our policy. We obtain kind of a series of constant factor approximations depending on the structure of the graph. If we have a general graph, bipartite graph, or if we have bipartite graph but one side of the market wants to leave immediately upon arrival. Okay? And then we can get an approximation ratio of 1 minus 1 over e. And the policy here is actually based on a rounding of the LP relaxation. So the LP relaxation that I mentioned, we can actually convert it into online decisions, on-the-fly decisions that will achieve these approximation ratios against the linear program. So how do we do that? So in some sense, the framework is quite similar to other papers in this area, that we solve this flow matching problem, the fluid relaxation. We get a fractional flow, and now we understand how to interpret this fractional flow in the way we're making online decisions. Okay, so that's the kind of the recipe. And for example, Amin showed this morning an interesting randomization strategy where the agents waiting, which were the resources, make matching proposals. They request to be matched according to some probability distributions, and then the analysis boiled down to understanding at which frequency these requests were made and were ultimately successful. And that led to kind of the analysis. So here, one element that is important is that our randomization strategy needs to encompass a notion of flexibility. And there's a very simple kind of reason to that. So what do I mean by flexibility? So let's think of the following thought experiment. Suppose that there is an agent to be matched. This agent is waiting, right? So what's very important in this setting that we're considering is that there's a risk that this agent will leave the system. So if I'm committing to only matching this agent to an agent of type A, it's not the same thing as if I'm pooling together A and B. If I'm waiting to be matched with a larger pool, if I'm less restrictive. So think of this threshold. If I have a very high threshold, there's going to be more people that I can match with. So I'm less likely to abandon because there's some pooling effect. Of course, this comes at having a higher threshold, so sacrificing a little bit the quality of my matches. So in this type of problems, one thing that is central is that we have this sort of pooling effect. And we want to build these pooling effects into the way we execute our randomization strategy. So this is, at a high level, kind of the ingredient, is that we will need to have pooling sets. We need to be able to pool arrivals in the way we run our policy. So how does it work? Well, we are given a solution of the LP, xij star, and we want to convert it into our decisions. So how do we do that? So first of all, remember that this xij, the ordering between I and j matters. I is an active agent waiting to be matched. J, we said, was a passive agent that would be immediately matched, or matched with someone who came earlier. So the first step of our randomization strategy is to try to mimic this separation. So when an agent shows up, an agent of type I shows up, I'm going to toss a coin proportional to the xij's, and based on that, so I'm going to sum all the active occurrences of I and all the passive occurrences, and based on that biased coin, I'm going to label the agent as either active or passive. And I'm going to only match active with passive agents. So I'm recreating a bipartite separation within the model. And this is directly governed by the LP solution. So I'm trying to mimic the proportions of active and passive matches I'm doing. Great, but now for the active agents, as we said, we want to create some pooling effects. So how do we create these pooling effects? Well, the randomization that we have here is going to be a bit more complicated than, say, for a standard kind of online matching problem. We need to do a randomization over subsets, not just over actions. So there's going to be this notion of compatibility sets, and each agent we're going to label with a compatibility set. The compatibility set will be a subset of passive types that agent is willing to match with and it will wait for. So this, if you draw this one versus this one will be more flexible. There's more agent that you can match with, so this way you can hope to reduce the exposure to abandonment because you're going to be more flexible. Now, how do we do this randomization? Well, it comes from the LP. So this is non-trivial. That actually requires, of course, quite a bit of work. But we can decompose the LP, convert the LP solution into a distribution of subsets that will be actually nested. And these subsets, we call the compatibility sets, will dictate how picky you are or not in waiting to be matched. And that will govern how much abandonment you're exposed to versus matches. So, and then the analysis will be based on analyzing basically the reward, how rewards are accrued in this process over time in expectation. And one idea, key idea, is to look at, to try to lower bound the availability of agents and use the pasta property, the fact that an arrival will be independent to the state of the system. So this lower bound actually, again, if you followed through this morning, will be very similar in spirit to what Amin presented. So there is a true Markov chain describing the process where and each time a passive vertex pops up, there could be multiple active agents who want to match because it fits in the compatibility set. So if this happens, that's bad. This is a conflict. This is a contention. So we need to kind of resolve that contention in our analysis. Well, we just assume that we're greedy, so that we pick the one that has higher reward, and we just ignore the fact that there is contention. We create something we call in the paper a virtual Markov chain. So imagine we could satisfy everyone. So they kind of go back to this idealized world where we can just focus on one agent and assume they can always be satisfied. So this is, again, a very crude approximation because we're just assuming that we have copies and we can satisfy all the agents. But doing so gives us a lower bound in the stochastic sense, on the availability of agents. So we can use that trick to analyze. And it turns out that this results in a loss of a factor of 1 minus 1 over e, precisely as for the algebra that we discussed this morning. Okay? So that's the kind of high-level picture. I don't want to delve too much on the specifics, but give you a flavor of the type of tools we use. And if there is any question on this.
Can you show the plot that you skipped?
Oh, sure. Thank you. That was, I was hoping someone would ask. So basically, we never tried, so this is, if I'm honest, this is a theoretical result, so we never actually implemented this policy. I don't know how well it fares. But the other policy I showed, this notion of thresholds, we sensed that this might be a reasonable policy. And in fact, we had kind of evidence that in the industry, these types of threshold policies are used. So we focused on the previous result, the sort of additive threshold policies or additive approximation of the value function. So we're taking the threshold, but now we're smoothing our decision. So where the value to go, the cost to go, it'll be the sum of the cost of all the agents remaining in the system. So these are the type of policies I want to test. We looked at some New York taxi demand data at different times of day, processed the data to create basically instances with a reasonable number of agent types, in a couple of hundreds. These are the number of agent types. And you can think of performance in two ways, right? Because inherently there's this trade-off. I want to achieve high quality matches, but at the same time, I might incur abandonment. So match rate is 1 minus the abandonment. That's the percentage of riders that would be matched ultimately, that don't leave the system. And the saving rate is once I'm doing a matching, when I'm carpooling two agents, so I didn't mention, but we're trying to simulate a carpooling system, I'm going to generate some savings because these are based on the route of the matching. I can understand how much distance I have reduced compared to like standard rides, solo rides. So that's the experiment we tested. And our results showed that basically, so I'm comparing batching policy, threshold policy, and vertex additive, that's the value function approach, on saving rate and match rate. So that's the y-axis and the x-axis. And why do I have multiple points? Because there's a tweaking parameter that I can use for the batching window. I can make it smaller or larger. And this means basically how much value I place on basically minimizing abandonments versus cost. Because if I'm increasing my batching window, I'm making people wait longer in the system. So what we see is that basically threshold is, so batching would be great if you want to achieve very high match rates. If you care about matching everyone or like a high proportion, then batching is actually a good policy. But if you're trying to think of savings, then threshold or vertex additive policies can achieve higher performance. So that's kind of the main takeaway. And why is that? So I don't have the plot here, but it goes back to this idea that some agents need to wait much less than others. Depending on where they're located, depending on the arrival rates, it's not the same. The graph does not have the same connectivity everywhere in the network. So this means that different agents have to be treated differently. That's what the batching window is not able to achieve. One caveat here is I'm not putting estimation error here. So in the sense that we have to, in the real world, if you were to run these things, you would have to estimate the arrival rates and the abandonment rates. I'm assuming here that I have good foresight of that. Yes?
Just a confirmation question. Since you're using New York taxi, so are taxi represented by any one of those vertices on the graph or not?
No, so this is a carpooling. So I'm matching agents with agents. There's no bipartite structure.
We're not sure, we don't necessarily care about how taxi comes up in this graph.
That's a great point. That would be, say, to make this model more realistic, I would have to represent that. But that's, for carpooling, that would be like more of a second order consideration. Yeah?
This might be quite related, but not exactly about the thing that you were discussing. But as I understood, you were discussing a centralized matching, like I'm Uber and I'm matching taxis to people.
Right.
A lot of platforms are not governed by some centralized matcher in between, but your threshold algorithm seems that's
excellent.
applied to such markets. So have there been studies, the performance and incentive compatibility for the setting that people match themselves to each other?
That's an interesting thought, and to my knowledge, no. One thing that we like about these policies is that they're kind of decentralized, like they're looking only at local information, so they would be amenable maybe to decentralized algorithm. We haven't pushed that direction. with Omer, we've been looking at actually decentralized pricing, because we thought that pricing might be a more kind of a core question for decentralization, because maybe the suppliers or the drivers in this market may want to kind of set their own prices. We have a work that is also in this realm of dynamic matching, but where pricing can be kind of controlled by, not by the platform, by the suppliers. Yeah. But these are interesting thoughts potentially for this work. Yes? Claire.
So if you're thinking about controlling your graph, your spatial graph is really a road network.
Yes.
So really you should think of this as this Euclidean distances or distances in a planar graph or something like that.
So these, so we don't need them to be Euclidean or to be embedded in a planar graph, but in practice that would be typically the type of settings where we would implement them. Exactly. And I think there's lots of very interesting questions, some of which we're looking at the moment in terms of, so this result here is not, we don't have a bipartite. There isn't servers and customers. It's like a matching where I can match anyone with anyone. So something we haven't been able to obtain in this work and we're kind of thinking about is now same type of metric graph or like spatial assumption, but having kind of both customers and suppliers, so like a bipartite structure. I think that would be a very nice kind of extension of this type of results. Yeah.
What I don't understand is if I think of controlling something like left-hand car, the people who connect, there are those who want a ride but they don't have a car, and those who have a car and they're looking for passengers. But you're saying anybody can be anything.
So I'm not entering that level of detail in the simulation. So these are ultimately synthetic instances, but that's a great point. So actually, in fact, in practice, you would have a higher proportion of people who are already in a car needing to be matched. So here, I'm kind of treating that exogenously. But these are all very important caveats for this. Yeah. Great. So with the time remaining, I want to tell you about a kind of slightly different story and thinking of another kind of deviation from the classic online matching problem that I think is also very important and interesting. And actually, I have also some kind of empirical results here that can motivate this. So I want to think about correlations and correlated arrivals, because the classic models do not encompass this type of properties. So, and this is joint work with my colleague Will and a kind of more recent paper. So I want to, first of all, kind of lead up to this notion, and with time remaining, maybe give a glimpse into how we kind of analyze this type of problems. But going back to the static, like the standard online matching problem, classic setting, so we have these offline agents waiting to be matched and online agents. So we're no longer in the realm of dynamic matching, and we have a bipartite graph. So this is what it looks like. So we have some resources with some inventory, and we have agents coming to the system. Okay. And the colors here are chosen in a kind of completely arbitrary fashion. So, we will be again having these rewards by making matches. So in a classic setting, so what we have is like basically a horizon. There's going to be T arrivals in the future, and in every period there's going to be an agent popping up, and the type of that agent will be revealed. For example, this is a red agent. Which means that, with this information, I know how much rewards I can hope to achieve by matching this agent, this customer, to any of the resources available. And I know kind of in advance there's a probability of appearing in the system. Okay, so that's the classic online stochastic matching problem. For every period, there's going to be a probability, and according to this probability, I'm going to draw the type, and based on the type, I'm going to have to make decisions. So I want to question one specific assumption that is running, it is kind of running through the literature of like serial independence. So this is typically assumed that upon each arrival, the type that is revealed is actually independent from previous realizations of types, conditional on knowing the information that I have about these probabilities. Each type, that new type that arrives, is independent. And this, I think, is motivated by Poisson type processes, where kind of new arrivals will be independent from previous ones. So now, there's many reasons to kind of question this assumption. So one is maybe there could be estimation errors. So for example, maybe I don't know exactly how many agents will come during the day or whatever my planning horizon is. So maybe I don't know this T, how many there are. And then maybe I don't know PT. And if I have forecast, there's a data scientist handing me kind of a forecast, it's very likely that the errors will be correlated across time periods. And this can induce some correlation. So that's one reason. The other reason that I want to argue that is quite interesting is that if I think about the demand, if I think about how many agents will show up after this whole process, this is a Poisson binomial distribution. For every type J, if I count how many agents arrive, this is going to be a Poisson binomial distribution, which has a number of implications, kind of implicit assumptions here. One is that the variance of that demand is smaller than the mean. And for many typical models in kind of textbook demand models, that's not the case. That typically we model demand as Gaussian distributions where kind of the mean and variance can be very different. And in fact, we have conducted kind of numerical checks on 2 data sets and looked at variance smaller than mean is actually not so frequent. So this is about e-commerce, looking at different SKUs, different products, and looking at how much drawing the demand distribution, looking at the mean and the variance. It turns out that 70% of the cases, for 2 independent data sets, more than 70% of cases, this assumption is violated. So in the sense that making this assumption actually imposes something that is kind of interesting to know. So I'm going to not go too much into the detail. And the last observation is that even if I'm only assuming serial independence, depends over time, in fact, I'm also getting nearly cross-sectional independence. Because this distribution is very close from Poisson, and as a result, for hard instances, for hard problems, when you scale T, you will also get cross-sectional independence. That in the sense that the demands, these DJs, will also be independent across types. So this is the setup for thinking maybe of different models that don't have these types of assumptions. This is why we propose non-parametric models that can maybe render correlations in the arrival process. And if there are correlations, then the implication will be that the variance of the demand and the mean, variance might be potentially larger than the mean, reflecting some of the observations that we have on the data. So the kind of idea for the model, so I'm going to introduce the model in a second formally, but at a high level what we're doing is forgetting about modeling an arrival process. So typically in the literature, we're trying to model the arrival process, what will happen in every period of time. Instead, let's try to think of the demand distribution itself. Let's think about the vector that counts how many agents of each type will show up. Okay, because ultimately, this demand distribution is also what governs my offline optimum. So if I'm looking at the whole problem and doing a replay and trying to look what was the best I could have done in hindsight, this would be completely determined by how many agents arrived, not so much about when they arrived. So it's a kind of modeling-wise, it's actually natural to think of modeling demand. But of course, if you don't have any structure on that demand, this problem will be actually as hard as it can be. So there is no hope to get any competitive ratio. So we'll have to add a little bit of assumptions and impose some restrictions on the demand. So what kind of assumptions do we consider? And of course, I didn't say that, but we have to also specify the arrival ordering. So it's great to generate a distribution for demand, but you still have to tell me how the agents will come. And here we'll make 2 stylized assumptions. Either it's adversarial, so nature is choosing the worst sequence, or uniformly at random. And why are we making these assumptions? These are kind of standard assumptions in computer science literature. And it's a way of saying, okay, let's leave aside this question of the ordering. Let's focus instead on what type of demand distributions we can model and still obtain competitive ratios. So we consider 2 models, and I'm going to focus on one of them. And both of them generalize the kind of classic setting. So they are extensions of the classic setting. So the first model, we call it in-depth. And I'm going to get into this model in depth. So, okay. So we'll assume that each demand type, dj, follows an arbitrary distribution. So this demand vector d has arbitrary marginals in terms of distribution. However, the demand types are independent. So across types, I'm keeping one of the 2 independences. So as I mentioned, like the original model had both cross-sectional independence and serial independence, but now I'm preserving only the cross-sectional independence, but I'm allowing DJ, so each agent, number of agents of each type, to follow any marginal, have marginal distribution that can be arbitrary and non-parametric. Okay, so how to think of this model? Think of independent regions. Like J's here, imagine they are customers from different regions. So the demands for these regions could be kind of independent, but then within a region, if you have a burst of demand, then that can be captured here because more demand might beget more demand. So if you have, say, a self-exciting process describing how much demand comes up at a particular, in a particular location, that could be captured. So there's another model that we look at that kind of looks at the reverse case where you maintain some form of serial independence but relax the cross-sectional independence. I'm not going to cover that model, but just to give you, again, a sense of the robustness of the framework of using linear programming and online rounding to guide our matching decisions, and surprisingly obtaining kind of results that match the best known results for the original model that I mentioned. So I'll focus on this in depth. So how do we typically think of these types of models? By looking at linear programming fluid relaxation. So I'm saying, okay, again, xij's are matches of I to j. So here there is no ordering, there's no active and passive agent. This is, we're back to the classic setting. And of course, I have inventory, so I cannot match more than Ka unit. And then for my j, imagine I replace the stochastic process or this demand by the expectation, the average number of demands. So it's a deterministic quantity, and this is a form of fluid relaxation. So this is the typical kind of relaxation. So unfortunately, we can prove that for this type of more general demand distributions, you cannot achieve a constant factor competitive ratio. So we cannot get 1/2 competitive ratio, we cannot get any constant. Okay, so we need to have a more realistic framework for analysis. So what we propose is a linear programming relaxation that we call the truncated LP. So the idea here is to tighten a little bit this very loose constraint by saying the following. So if you think about how I match I to j, well, there is a natural upper bound on how many matches can occur. I cannot match more than the number of agents available, whether it's the short side on the resource side or on the demand side. So this is a cardinality constraint on the number of matches. So this is simply Hall's marriage condition. And then I can take an expectation. So for every set of resources, I will have such a constraint that the expected number of matches cannot exceed this quantity in expectation. And this is, again, Hall's marriage condition and then taking expectation. So by doing that, we're taking our linear program and we make it more realistic because it captures the kind of the fact that the demand might be correlated. And in fact, by doing this tightening, what we are doing is we are restricting the feasible region of the linear program. And by the way, this doesn't need, like this always holds, like this type of constraints, they're always true, even for the classic model. So it's only kind of making this benchmark tighter. Now, of course, the natural question is, can we really add these constraints? Because if you think about the number of constraints, we're adding a constraint for every subset of resources, S. So there's exponentially many constraints, but fortunately, this is actually something we can solve. So not only it gives an upper bound on the offline optimum, but it's also, we can solve it in polynomial time because these constraints are well behaved. They form a polymatroid. So actually, this does not make, solving this linear program now does not make, it's not much more complicated. Or it is more complicated in practice, but at least theoretically, we can solve in polynomial time. Now, yes?
When you say you can solve it, like you have a separation oracle?
With the separation oracle, exactly. So the polymatroid constraints mean I have a separation oracle.
Okay, so did you try to implement
So the nice thing is you don't need to solve this LP to generate policies that have the same guarantees. That's something that comes later. You can actually just do Monte Carlo on the offline. Like you can simulate a bunch of demand vectors, solve the matching, and then take the average. That would also be another way of getting the results. So in practice, you might not solve this, but you know, we'll use the constraints. I'm writing it because we're going to use the constraint in the basically the way we analyze the policy. Okay. Other question? Yeah, Claire?
So if I look at the left LP, fluid LP, what would happen if instead of writing expected value of dj, you wrote a particular value which would be obtained by just sampling and finding one particular drawing from this distribution and just putting this
One draw, one sample.
one draw.
I don't think that that's a great question, and there is some literature that is capable of, from one sample, kind of achieve competitive ratios comparable to the ones that Amin mentioned this morning. We don't know how to do that. We have been studying the sample complexity. That's one of the open questions that I mentioned at the end, but actually we have some results on that. So one sample would not suffice, but we think that the polynomially many samples would suffice. Yeah, so I'm happy to talk more about that offline. But that's, of course, because if we leverage this information, then we need to know what's the cost in terms of sample complexity, and we don't have a definite answer, but we think it might be polynomial. Yeah. Great point. Good. So we have a new LP. So Tristan would say that's nice, but you know, if you don't have an actual matching policy and kind of guarantee, that's not so useful. So what can we say about it? So well, I'll start with the negative result, and that shouldn't be too surprising, because this model that I presented is actually a generalization of the classic online matching problem. So you cannot do better than 1/2 competitive ratio. So that's the same upper bound as the one that Amin mentioned this morning in his talk. And in this case, actually, it holds even if you have a bit more structure. Like if you have large inventory, typically when you have a lot of inventory, you can basically redeem bad decisions so that you can achieve better competitive ratio. But in this case, that's not happening. And even if you have uniform arrivals, and that's much harder to prove, and that's work with a PhD student, Weizhong Zhang from CMU, where actually we can show that even if the arrivals are not adversarial, even if they're well behaved and they're uniform, this 1/2 competitiveness holds. So that's the best we can hope for. And the positive result that we have is that actually there exists a matching policy that is 1/2 competitive. So achieving that upper bound. And in some sense, extending the results that are known for, the similar results that are known for online stochastic matching. Okay, so, and this policy will be based on our linear program. So I'm not going to have time to cover this, but I will just tell you that what is underlying this is another form of online rounding. So actually, the surprising phenomenon that we observe is if you look at this new linear program, there's a way of converting this linear program into online decisions without loss, in some sense, in a lossless way, in some sense. So, and that's what this lemma is saying, that's a central lemma, is saying that give me any vector that is in this polytope, and I don't know how much demand will show up of a particular type, but I can route this demand to the different resources at rates exactly equal as the vector that you gave me. So the xij is actually happening, okay? Now, of course, actually, we still lose 1/2 because there is still some contention to resolve because these matching proposals, as I mean, like they might still conflict, and that's how we lose the 1/2. But that's actually, for us, was quite a surprising result. So adding these constraints not only kind of made the LP tighter, but now on the reverse direction, these constraints are sufficient. If you're just looking at one type of agent, they are sufficient to describe all possible, only feasible policies. We can convert them into feasible policies. So the rounding itself, you know, so what it looks like, I'm going to skip that because I think it is a bit ambitious. I think the whole thing was ambitious, but there's a nice visual proof, and I refer to kind of a paper for thinking more about that. But the idea, what's I guess surprising about this routing is like this is a visual representation of, let's say, you have 4 potential customers coming, and these bars represent the probability at which they're coming. So with probability 1, there's at least 1 agent coming. With probability 1/2, 2 agents. That's the DJ. So this is a distribution for the DJ. So typically, when you do rounding, what you do is you try to do proportional rounding. So proportional rounding, greedy rounding first. Greedy would be, you know, I have to match. Suppose that my x vector tells me I have to match with the fraction 1/8. Then let's just match the first arrival with the fraction 1/8 greedily, because I need to satisfy that fraction. So let's do it from, say, the first arrival. But that's not going to be good. And for this example that I cooked up, this is because if I match with a fraction 1/8, then this third entry I can never satisfy, because 7/8 plus 1/8 plus epsilon is greater than 1. So it's never going to happen. So greedy is not good. The other more natural approach is proportional rounding. So every time an agent comes up, I'm going to proportionally to the x vector try to match. That also is not going to work for this type of problem without loss. And in fact, it turns out that the best rounding, or like the rounding that is lossless, is by deferring, by postponing your rounding decisions as much as possible. So this is a very high level kind of comment. I'm happy to answer any questions for those of you interested after the talk. Okay, so just kind of to wrap up, so we looked at essentially in this talk 2 kind of extensions or variants of online matching problem that were capturing different aspects of real-world matching systems. One was about modeling the dynamic arrivals and departures, the fact that the market has certain thickness, and that thickness is in some sense endogenous to the matching decisions that you're making. And the second was looking at correlated arrivals, so thinking beyond the serial independence assumption. And quite surprisingly to us, actually, there's quite some evidence that correlations do occur in real-world matching systems. So maybe more to do in that area. And I think some of the common principles that arise from this is thinking about beyond fluid relaxations. So thinking about mathematical programs and relaxations of the problem that are more realistic, closer to describing the real underlying MDP. And that meant adding constraints, generating more constraints into the problem. And the kind of from an analysis perspective, what we did is showing that there's an attainability result. So we can actually mimic the solutions from these linear programs or extensions by real policies and closing the gap or leave up to a constant factor. And I think there's quite a few very interesting directions for research in this area. One is for the dynamic matching model that I discussed, 1 minus 1 over E is the best we could achieve in bipartite graph with one impatient side. So it would be very nice if we could kind of breach this ratio. And in fact, follow-up work by Amin, Tristan, and co-authors showed that you have to use a different linear programming benchmark. That LP, for that linear program, the integrality gap is 1 minus 1 over E. So you cannot hope to achieve better than that. And then a question that was pointed by Claire about sample complexity. So how many samples do we need? If we were to model more complicated arrival processes, of course this comes with needing more data to be able to estimate these models. And then one area that I think is quite interesting is thinking of stochastic structures and correlation structures that come from predictions uncertainty. So thinking about the fact that many of the model primitives here come from some data scientists proposing a prediction algorithm, and that in some sense shapes the uncertainty that you're facing. All right, so thank you all, and I'm happy to take questions.